Introduction, and let me say how happy I am to be invited to Battery 2030 Plus and to have the opportunity to share our work with you. So thank you so much for the invitation. I will start sharing my screen. Okay, am I in screen mode?
Yes, perfectly.
Okay. So I'll be talking about halide and oxyhalide solid electrolytes today, as the title implies. And first, I'd like to thank all of our funding agencies for their support. And I will thank them again at the end. So, because so the talk is sort of a combination of electrolytes and also solid state batteries. And I'm sure that I don't need to remind most people in this audience of why solid state batteries are important. They're motivated by safety, energy density, and of course, operating range. And safety, there's just a few pictures of a battery plant that burst into fire just about a year ago. And of course, we've all heard about the problems with e-bikes being charged indoors. And these are, of course, all created by the problems of liquid electrolytes that have the usual safety concerns that we're familiar with because of the flammability of the electrolyte. And of course, the solid state electrolyte lacks these flammable, at least an all solid state electrolyte, lacks these flammable components. And the problems are really more one of interfaces. And so in the solid state electrolyte, which is really the key in the battery, we have to achieve fairly high conductivity for the solid electrolyte, at least more than 1 millisiemens per centimeter. And we have to devise materials that have stable interfaces and are ideally ductile, because getting those interfaces with the cathode materials, which can be a variety of either lithium, sodium, or other materials, is of course critical. And I just want to point out, especially since many of us live in a cold country, that it's not just a question of improved safety, but also these solid state batteries really exhibit a good low and high temperature performance, particularly good low performance, temperature performance, because we don't have to deal with just the viscosity of liquids at low temperatures, just simple Arrhenius issues. So aside from these positive attributes, there are many challenges, and I've just listed 3 of them here. We have to try to figure out how to lower the cell pressure. We have to also lower the cost of manufacturing, and also in particular try to increase the scalability of these materials in order to make them competitive with the liquid systems. So if you think about a liquid battery, these have been around for a long time. These have been carefully designed to, for example, have a solvent, usually more than one alkyl type carbonate solvent, some sort of salt, and additives to control the interfaces. And so this is fairly well established. This is an example of a quasi-solid state battery. This is a picture from QuantumScape. And this is the cell discharged as manufactured. And so the cathode side also has a liquid electrolyte, but on the anode side, there is a separator of some conductive ceramic. And this cell is designed anode-free, such that the lithium then comes from the cathode and deposits through the separator onto the current collector. So it's a conventional cathode with a conventional liquid electrolyte, but the difference is the ceramic ion-conducting separator. In contrast, in an all-solid-state cell, as I said, there's no liquid. And so we have to worry about how to design for high ionic conductivity, electrochemical stability at the interfaces, and also worry about these mechanical properties that are necessary to really sustain the cell through the redox cycling and volume expansion contraction effects that we have. So what are these design principles? So if you think about what has been gone into a liquid electrolyte cell, where really a lot of molecular engineering is used to devise these solvent concentrations. We go through the ceramic solid state separator in the quasi-solid state cell. We might want to think about, instead of using a conventional solid state electrolyte, move to, which are usually solid state ceramic type materials, we can think about moving to quasi-molecular systems. And that's kind of the theme of today's talk. So here's an example of a state-of-the-art all-solid-state battery of Samsung's. It uses a nickel manganese cobalt cathode. a conventional cathode, and agurite as the electrolyte. And this is a lithium-free cell, so this is resembling that anode-free cell in the previous slide, except what Samsung has done is taken a silver carbon composite layer here to achieve their anode-free configuration. So this is just the agurite that's sitting here, both as the separator and as the catholyte on the cathode side of the cell. And this was published in Nature Energy in 2020, and it's a really excellent example of an anode-free solid-state cell. But agurite has quite a few challenges, and one of them, in addition to many advantages, I should say, but it's one of its challenges that it has a fairly narrow electrochemical stability window, so it oxidizes at about 2.5 volts versus lithium plus lithium. And this means that such configurations need to have a coating on the cathode in order to inhibit that oxidation and stabilize that interface. And these coatings, quite a plethora of them exist, usually lithium niobate or lithium zirconate, but they can be difficult to apply. It requires an extra processing step, and they don't necessarily achieve ideal coverage. So it's something that one would like to avoid. And one can do that by using these chlorides and oxychlorides, which have, according to calculations carried out by Garrett Cedars Group in 2015, oxidation potentials that make them compatible with the NMC materials and other type of high voltage cathodes. So these are soft, the sulfides, but they're reactive. And the point is that the halides are just as soft. In fact, they have better mechanical properties in many respects, and they're stable. And they were introduced by a group at Panasonic, Sano et al., and they took this lithium yttrium chloride and effectively ball milled it to increase the conductivity towards that benchmark of 1 millisiemens per centimeter. And this caused a lot of excitement, I think, when this paper came out. And this is just an example of the lithium yttrium chloride structure. And you can see that there's 2 sites that lithium occupies, both octahedral and tetrahedral in this lattice. And that in itself causes a few problems. So since 2018, when this lithium yttrium chloride was first published, we've come up with there's been a lot of materials that are published, way, way too many for me to decorate the slide with. So I've just listed a few examples here and our contributions in red. So we published on some of these layered materials, but also this interesting spinel, which was we published that in 2020. And since then, we've been able to remove some of the expensive elements through a great collaboration with Nissan and Dr. Chandrappa and my student Yubo Wang worked together with Vanis carrying out some elegant calculations and Yubo carrying out some elegant chemistry, and we've managed to get this a new formulation on the basis of these predictive calculations and synthesize this other spinel. But I won't really have time to get into that today. So most of these materials, and this has the same conductivity, in fact, as the parent. But the point is that most of these materials have conductivities around 1 to 4 millisiemens per centimeter and hardness values about 2 gigapascals. And as I said, I can't possibly decorate this slide with all of the people that have contributed to this field, but I just wanted to highlight 3 publications which are particularly interesting on these materials down below. So on the subject of this spinel, and actually materials in general, not just the spinel, the requirement of a solid electrolyte is not just high ionic conductivity, but also very low electronic conductivity. And this is one of the things that gives rise to a high electrochemical stability window. And so my graduate student, Liedong Zhou, who's now a professor in China at Nanjing University, carried out some very careful electronic conductivity measurements on a host of these different materials. And you can see that they all have very low electronic conductivity in the vicinity of 1 or 2 times 10 to the minus 11 Siemens per centimeter. And what this means is that it becomes more difficult to actually carry out the electrochemistry on the electrolyte because it is so insulating, sort of like Lipon. So it really renders it resistant to degradation. And this is just a sample of this picture of a cutout of this spinel lattice, and you can see the pathways for migration as the lithium moves from the octahedral, tetrahedral to octahedral sites. And this is a somewhat a limiting factor simply because the energy of these sites is different, so it causes a more convoluted landscape for that lithium migration. But it is a low energy phase sharing arrangement, which is beneficial. So we carried out a lot of work on this material, and this is an example of its stability. This is cells under a little bit of under some pressure, but you can see that the cycling stability of these cells is really very good. This is over 700 cycles. We're getting almost the normal typical capacity we would get in a liquid electrolyte system from this configuration with good coulombic efficiency. And we can even, Lidong was able to increase the loading in these cells up to about 21 milligrams per square centimeter and achieve aerial capacities in the order of 4 milliamp hours per square centimeter, again with excellent coulombic efficiency. And as I said, this is by virtue of its very low electronic conductivity, and this drives this high kinetic overpotential. And we've been able to cycle these cells for 100 cycles or so, even up to 4.8 volts, which far exceeds the thermodynamic redox oxidation potential, which is in the order of 4.2 volts. So this works because if you compare this with an agurodite type cell, where you have the cathodes coated, as I said, to protect them from oxidation, in this case, the electronic transport through the cathode composite is somewhat limited by these coatings. Whereas in the case of the chloride electrolytes, where you really have a patchy sort of coating, which can be seen here in these elemental maps, you have a patchy coating, and the cathode materials are simply compressed together, thus forming a continuous electronic pathway. And the lithium from the electrolyte then feeds into the system, as shown by the blue arrows, through this patchy type coating. And as I said, the low electronic conductivity of this electrolyte, shown here in green, renders it somewhat resistant to any electrochemical oxidation. And so these are all of the important qualities. So we worked together with Jürgen Janik's group, the Justus Liebig University in Gießen, to try to understand the nature of these interfaces a little bit better. And sort of our general combined approach is shown here in this diagram. So what we decided to focus on was 3 of these metal halides: a lithium indium chloride, a yttrium zirconium chloride, and our scandium indium chloride. And you can see here on the left that whereas, and we abbreviate these, and so this one is called Liebig because it's easier to say. So you can see that this has very stable cycling, the one I just showed you, whereas the lithium yttrium zirconium chloride really behaves rather poorly. And so we carried out, Jürgen's group carried out TOF SIMS, we carried out DFT, we did all sorts of ultraviolet spec. We basically did a lot of different measurements, let's just say. And we were able to sort of understand why the Liebig is stable, whereas the LYZC is not. And that is summarized on this slide. So in my group, we carried out these DFT predictions of chemical decomposition, and we used lithium nickel oxide, or charged lithium nickel oxide, as a representative for NMC because we can order the structure. And we then compared the lithium indium chloride, the Liebig, and the yttrium zirconium. And you can see that the reaction energy for that at the interface to form either the oxychloride or the zirconium oxide is negative in all cases, but it is definitely most negative for the yttrium zirconium chloride. This is the point at which the NMC undergoes its H2 to H3 transition, phase transition, and evolves oxygen. And so what we think we form is a passivating layer in the case of the indium, the LIC, and the Liebig, whereas there is a continual formation of insulating zirconium oxide in the case of the lithium yttrium zirconium chloride. And you can see this by comparing the TOF SIMS results, and these are sort of a cartoon of the data just because it's easier to see. But if we compare the pristine cathode active material with the cycled, you can see in the case of the LYZC, there is a strong indication of formation of oxychloride. We see a little of that at the start just because of some moisture in the chamber, but that intensity increases on cycling. And this is the characteristic feature of this reaction. We can't actually see the zirconium in the case of top SIMS because it's not very sensitive. So we detect the formation of the zirconium via the formation of the oxychloride. In the case of the lithium indium chloride, we see a feature of the indium chloride fragments, which indicate some electrochemical instability at that potential. And again, that's not really surprising. But you can see in the case of LISIC, which really functions the best in terms of cycling stability, that there are no traces of either oxychloride or the metal chloride. So this is coincident with its electrochemical stability. And so this is just showing that this is the feature of the electrochemical instability. This is the feature of the oxygen reduction, whereas we have a stable unlisic material. So it's not just the question of the metal chloride itself being stable at the interface. The nature of the metal in the metal chloride is important to interface stability, is the conclusion. So just another side point, there was a really nice paper by Shirley Mung's group in Science in 2021 showing that one could use micron-sized silicon particles as an anode instead of lithium indium, which we typically do use. And this also forms a stable interface for the agurodite. But they did see low initial coulombic efficiency and not ideal utilization of the cathode material. So what we did was we pre-lithiated the silicon anode simply by a very simple reaction between the lithium and the silicon. And you can see that the initial coulombic efficiency is increased significantly compared to the silicon system. And so we ran cells then in this configuration, similar to what's shown here with the lithium silicon anode, a layer of agurodite, and then our lithium metal halide as our both our interface and also our catholyte. And in this case, we were able to get very high aerial capacities as shown here, but also as shown here. So we're upwards of 16 milliamp hours per square centimeter with a very low negative to positive ratio of 1.2. And of course, this is not at high current density because we're loading about 81 milligrams per square centimeter of cathode active material, but this is sort of proof of concept. So let's switch gears from lithium to sodium. And we have to, in the case of sodium, there's the analogous halide materials. This shows a sodium yttrium zirconium chloride, also reported by Shirley Mung's group. And this has really, the sodium materials tend to have much lower conductivity than their lithium analogs. But they still function fairly well in cells. This shows the equivalent of an erbium zirconium with similar conductivity. And this is just a paper by from Jürgen's group where they swap out a sodium antimony sulfide, which is a very, very highly conductive material, with this halide. And they actually see improved cell performance despite the much lower conductivity of the halide. So just like in the case of the lithium halides, these have a high oxidation potential, which is very beneficial. But as I said, they have lower conductivity. And in great part, this is because of the larger size of sodium compared to lithium, which creates a bottleneck, in particular for crystalline structures. So the first few of these that were reported, the one mentioned here, and also a variation on lithium zirconium chloride with a higher conductivity. As I said, these are all crystalline materials. And just this last year, because we're in 2026 now, there were 3 very interesting materials reported based on an amorphous structure. And the amorphous nature of these materials seems fairly critical to inducing better, we'll say, conductivities. And in fact, this group, Shah's group, even got up to 3.4 millisiemens. So that's kind of exciting. And we started our work last year as well, trying to use a similar approach to developing new materials, not necessarily crystalline, but quasi-crystalline or nanocrystalline, or as I said, fully amorphous. So this shows our new zirconium-rich amorphous fluorochloride. So instead of using just a chloride, we decided to incorporate fluorine into the material in order to increase its oxidative stability. And so this shows the optimum composition, which is simply obtained by ball milling for a few hours, not a very long period of time, sodium fluoride. zirconium chloride, and tantalum chloride, and the tantalum chloride can be replaced by tantalum fluoride. And these components are important partly because they sort of dope the lattice, although it's not clear that one could call that doping, but because it's an amorphous material. But they also are fairly low melting materials, solids, which when ball milled effectively act as a solubilization matrix to solubilize these salts. And so that means that the ball milling process can actually be fairly, short. And this has just come out in ACS Energy Letters, I think, today. So this shows the synchrotron pair distribution function of the apparent zirconium chloride, which is shown here in the dotted blue lines, and that of what we call NZT, which is the sodium zirconium tantalum chloride. And you can see that we lose long-range order at about 8 angstroms almost completely by comparison to the parent. And so we think that what we're forming by this reaction, which is at room temperature, but probably slightly warm because of the ball milling, is that we take the parent structure of the zirconium chloride shown here, and effectively the fluorination breaks these chlorine-chlorine edge-shared bonds, and we probably form linear fluorine arrangements between the metal centers. This is either the zirconium or the tantalum, and so effectively we open up this structure. But it's obviously oligomeric and probably short chains. It just spans a few metal centers because of the lack of long-range order. So our conclusion is that we have these sort of short oligomers of these metal halides. And so this takes, if you compare NZT, which is the zirconium, with the same sodium concentration, but without the tantalum, versus just this sodium chloride, zirconium chloride, which was reported last year, you can see that the conductivity increases significantly from the 0.11 millisiemens of the so-called parent material to around 1 millisiemens for this tantalum dope material, and of course the activation energy drops accordingly. So as I said, it's a little hard to just talk about sodium vacancy creation because it is an amorphous material. It's fully amorphous, but we can think of it in those terms as increasing the conductivity. So again, we have a matrix, an amorphous matrix of these short chain oligomers that are effectively weakly coordinated to the sodium. And we know that they're weakly coordinated to the sodium because of NMR, which was collected by my postdoc in Young Chui. And all of these materials, we've looked at this is the parent material, which I mentioned, the NZT. We have this more highly fluorinated version, which we obtain by reacting the parents with the tantalum fluoride. And we've also done hafnium just as a sort of a proof of concept or a check on the system. So you can see that the conductivities are all really fairly similar, and what's surprising is that this very highly fluorinated material has a conductivity really quite not far off that of the less fluorinated material. But they all show a single feature in their sodium-23 MAS spectrum, and that happens to be the same chemical shift as reported for this this crystalline sodium chloride. By Meng's group in matter. But what's more important is not the fact that it's a chemical shift. What's important is this T1 relaxation time, which is really quite short. And so that is indicative of fast sodium dynamics. And that got us quite excited when we saw this. We think the environment of the sodium is either 7 or 6 coordinate, but it's hard to tell at this point. So this fluorination increases the oxidation stability up to 4.5 volts versus Na plus sodium. And here we just compare a CV with our previously reported sodium tantalum oxychloride, and I'll be talking about oxychlorides later. But suffice it to say at this point that we have a distinct increase in that oxidation potential, which is beneficial for high voltage cathodes. And this just shows the charge discharge profile for this material with with a sodium vanadium phosphate. And what we're using here that's off the screen. We are actually cycling these materials with sodium 15SN4, the alloy, as our negative electrode, and we have to put on an interface of this hydroborate to basically stabilize the halide against the anode, against the alloy, because the chlorides reduce at a fairly moderate or high voltage, so that we have to protect this negative interface. And so then with this sodium vanadium phosphate, NVP as we call it, we see very stable cycling capacity, well over 300 cycles. And we can even take this up to higher voltages to 4.4 volts using a variation of this NVP, which is a higher potential. So the take-home message here is that we have intrinsically higher oxidation stability of this, our sodium, zirconium, tantalum chloride, owing to the fluorination, and good stability with high-voltage cathodes, such as this, or the oxyfluoride. So then I will switch gears again now to the oxychlorides. And these have the conductivity of sulfides and stability of the halides. This diagram comes from this paper by Tanaka, published in Avanti Chemie, also Panasonic. And this shows the conductivity of the lithium tantalum oxychloride and lithium niobium oxychloride, which they are reported on, compared to some other materials such as agirrodite, LGPS, and some of these halides. And so you can see that really the conductivity is very high, similar to that of the sulfide. And but as I said, the stability is basically the same as the halide. And there's been other reports of these amorphous, and these are again amorphous, like the halides I just mentioned in the case of sodium. And these include a fluorochloride, a gallium fluorochloride reported by Samsung, and a lithium aluminum oxychloride reported by Yongsheng Hu's group, and also by Andy Sun's group, and recently by Kyusuk Kang's group. And so these all have, on the lithium aluminum side, these all have some component of lithium, aluminum, oxygen, and chlorine. And these materials all seem to be a little bit different, as is ours, which I'll be talking about later. So take-home message here is that these materials they can have high ionic conductivity in the case of the niobium and tantalum materials, less so in the case of aluminum. They're actually very soft, and I'll be discussing that at the end of the presentation. And oxidative stability allows good contact with cathode active materials without any coating, just like the halides. So I'll be talking about two of these today, the lithium niobium oxychloride and the lithium R version of the lithium aluminum oxychloride, which differs in its oxygen to aluminum ratio from that reported by Andy Sun and Yongsheng Hu and Andy Sun, and also by Kyusuk Kang's. And as I said, I'll be talking about the mechanical properties of materials in solid-state batteries towards the end. So we were quite curious about this paper that was reported by the material that was reported by the Panasonic group, and so we decided to repeat the synthesis of the material, and we were able to achieve the same conductivity that they were, upwards of 11 millisiemens per centimeter. And you can see from the neutron diffraction pattern that this is a nanocrystalline material. It's really, the peaks are quite broad. We still can do a refill refinement, but it's kind of an average structure. And we carried out our refinement in the CC space group, unlike what they did, because, as I said, this is an average structure. And from the negative Fourier density map, which is specific to the negative scattering length of lithium, we were able to identify 6 sites, which are shown here, of the 8 that were predicted in the lattice. And we carried out AMID simulations, and these show really very high diffusivity. This shows the probability, the isosurface at 300 Kelvin and at 600 Kelvin. And you can see that even at 300 Kelvin, it's just a very good dispersion of the lithium. And a diffusion coefficient we calculated of 5 times 10 to the minus 7 centimeters squared per second. And this is 5 times that of agirrodite. So this is a very, very highly conductive material. And the calculated conductivity of 17 is a little higher than that experimentally, of course, but that's to be expected. So this is an interesting material. It effectively has this chain-like structure, which resembles that of the two-dimensional material, which is niobium oxychloride. And niobium oxychloride is effectively a van der Waals solid because there's very weak bonding between these sheets of niobium oxychloride. So you can think of lithium niobium oxychloride as simply this material plus lithium chloride, where the lithium disperses in between the layers, and the additional chlorine ends up modifying the coordination of the niobium. And if you look carefully, you can see that these sites are very there's a very low population of lithium on these sites, and so these sheets are not exactly van der Waals bonded because there is electrostatic interaction of lithium, but it's quite weak because of that low degree of population. So this is key to this material's conductivity, and our NEB calculations show that there's an activation energy about 0.25 in the BC plane, which is this plane, and 0.14 along the A-axis. In other words, in this direction. So this is a very, very low activation energy. So overall, we have three-dimensional lithium diffusion and a very low energy barrier. We have these fairly weakly bonded sheets of niobium oxychloride with lithium free to wander in both the AB plane and along the C-axis. Now, this freedom translates into some very interesting anion dynamics. So this shows the octahedral deformation of the NbO2Cl4 units, which are effectively these units. And so you can see that the niobium chlorine angle is actually quite wobbly with it wobbles by about 24 degrees. So there's fluxionality in this plane. And also the niobium oxygen bond is also wobbly with a wobbliness in this direction by about 20 degrees. And this is shown at 300 K from our AMID calculations. So we have a really dynamic range of angles, both for the niobium chlorine and the niobium oxygen. And just as interesting, if not more so, is the fact that we also have an interchange distance variation. So in other words, if you take a look at this, the planes, these sheets of niobium oxychloride, we have a distance variation in the lattice by about 1.5 angstroms from its average value. So that represents about a 15 angstrom wobble in between the sheets. So these are really very mobile materials, and we call this the flexion concept, which is that we have highly functional chains, which basically flattens the energy landscape for lithium diffusion in all three directions in this material. And this is nicely caught by a picosecond snapshot where you can see the degree of wobble for the chlorine in this direction, the oxygen, which is shown in red here. And this is then coincident with the lithium translation over these 8 picoseconds from one site to the other. So this is not a paddle wheel. This is really what, as I said, we call a flexion concept. And there's no evidence that this is a correlated motion, so to speak, but there's obviously some degree of connection between this fluxionality in the anion and the degree and the movement or the mobility of the lithium. And you can see this by thermodynamically incorrect, but nonetheless useful situation where we freeze the lattice. And this is shown in orange. So in other words, there's no fluxionality allowed versus freeing the lattice where you can see the MSD, the mean square displacement of the lithium now, is really quite significant over this time frame. So I sometimes like to use the analogy of these hula dancers with their grass skirts. And if one was trying to move through this assembly of these young men and their grass skirts were not swinging, you would be sort of stuck with these little, these unpleasant interactions. Whereas when the skirts swirl, mobility of the lithium or a person through this is going to be facilitated. And the theoretical prediction of our limiting activation energy of 0.25 eV is nicely borne out by experiment. This is the value that we achieve at 20 degrees to 70 degrees. And you can see that this is variable. And as we get down to temperature, the activation energy increases. And this, again, is coincident with this cooperative motion of the anions. So this is the take-home message that I would like to mention. And just this works perfectly well as a cathode up to about 4.3 volts. We have aerial capacities attained up to 4.8 milliamps per square centimeter and good cycling performance up to 550 at 25 degrees. I might add that this is not quite as good as we see in the case of the halides, but these cells are under a lower pressure. And just to make a point about this low temperature performance, this is a modified lithium titanium oxychloride, but it's basically similar. And this shows a material with a conductivity of 9 millisiemens, loading of 8.7 at a C rate. And you can see that even at -20, we get really very reasonable capacity out of the system. Whereas in the case of a chlorine-rich agiridite, which is the most highly conductive material we could prepare, which up at 10 millisiemens, similar loading, and even at a slower rate, we're nowhere close to that at -20. So this shows the benefit, especially as a catholyte, of having a highly conductive material. So now I will switch gears again to now move to the aluminum system, which is a new class of these solid electrolytes, which are effectively oligomeric molecular ionic solids. And in some ways, they're similar to the sodium zirconium halides that I mentioned, except, of course, they're made by a very different process, and they're oxyhalides. So we took the concept of a silicon-based molecule, which is this material, and we simply replace the silicon with lithium and aluminum. And this forms these oligomers, which are, we believe, to be isostructural with their silicon analog. And this is done by a fairly simple process, whereupon we carefully hydrolyze the material. This releases hydrochloric acid, and this reaction is carried out at 180 degrees, and the hydrochloric acid is simply pulled out of the system via vacuum. And so it's a very scalable process. As I said, we use a different aluminum to oxygen ratio than the other groups that I mentioned, Yongsheng Hu and Andy Sun use, and Kiso Kang. And whether or not these materials are all similar or not is kind of an open question. But anyway, we have a conductivity that's around 1.3 millisiemens and a transference number that is in excess of 0.98, whereas some of the other materials, were transference numbers were much lower in the order of 0.69. So that's why we think that this is a different material. And this just shows diffusivity data collected both from EIS and PFG NMR, showing the PFG and EIS data are right on top of one another. So the coordination of lithium in the system is quite interesting. This just shows some solid-state lithium-7 NMR data, comparing lithium aluminum chloride with a lithium aluminum oxychloride, which has 5-coordinate lithium with our material. And again, you can see one major peak here with a coordination number. We assign this a coordination number of 5, and this comes from data of Max Rosinski, which basically shows that there is this consistent shift in frequency as you go from 6 to 5 to 4. This was for a different class of materials, but it holds for these as well. And you can see that the T1 relaxation times are slower for the 4 and the 6 coordinate system, where it's much faster for this 5 coordinate center, which dominates. And we were able to see this 5 coordination by doing the AMID simulations. This is Dr. Singh in my group, Voltage Singh. And this dynamic nature is, we believe, because the lithium is coordinated in a dative fashion to the oxygen in the lithium aluminum oxygen in this aluminum oxychloride chain, and in a sort of somewhat more ionic fashion to the 3 chlorines. So we have a sort of a lone pair donation to the lithium from the oxygen and a weak interaction from the halides. And we believe that this is what is underlying the nature of this dynamic response we see in the NMR. And so this mixed anion coordination is vital to the lithium diffusivity. And again, AMID carried out by Baltesh Singh, my postdoc, shows that we have a calculated conductivity in the order of 2.8 millisiemens, which is really quite similar to what we measure. And this shows the lithium isosurface and the chlorine isosurface. You can see that there is, again, very high diffusivity of the lithium in the system. This is borne out in the MSD, both at 400 and 600. And you can also see that at 400, there's even some mobility of the chlorine, but this is not translational mobility. This is actually the oligomer sort of flopping around, as best one can say, in this environment. And this is, we believe, what this rotational motion of the trimer is what gives rise to its plasticity at a glass transition temperature about -15. And this plasticity can be seen here This is a material before we T stands for plasticized. We add a little lithium aluminum chloride to plasticize. And you can see that when you heat it at 180, it becomes a sticky, gooey material. And this is absolutely viscoplastic, not viscoelastic. And I'll just move over here. This compares the conductivity with pressure for lithium aluminum chloride, the agurudite, for example, and our layoc. And when we release the pressure, the conductivity for layoc remains the same, whereas, of course, it drops for agurudite and for lithium aluminum chloride. And we can simulate a modulus, which is on the order of 3 gigapascals with a yield strength of about 0.15. And I'll get to the mechanical properties in a moment, because I'm almost running out of time, but I have just a few more slides. So again, very promising cycling stability for these materials. This shows the data at up to 4.6 volts, where we see some fading, whereas at 4.3, we really see remarkably stable performance. This is under pressure, but it's at close to room temperature. And the utilization is very good. This case up to 200, it's about 208 milliamp hours per gram, and a very stable system. We use agurudite as our interface because layoc, like the halides, is not stable to reduction. So then in summary, just comparing these longer chain oligomeric materials like LNOC, we have high diffusion coefficient, we have low activation energy, and long-range diffusion. Whereas in the case of the layoc, we have done some Quenz measurements together with Dr. Mamontov at ONRL. And these Quenz, basically over a short range, because we're limited by the spectrometer, show that we have very fast short range diffusion in the order of 10 to the minus 6 centimeters squared per second. But the PFG NMR shows that we have slower diffusion on the long range. So we have local high mobility, but a long range diffusion coefficient a little bit slower certainly than the oxychloride, but not slow by any means. So then we can come up with a sort of a scheme for diffusion in this material where we have these 5 coordinate type centers, boosted lithium diffusion through these paths, pretty good diffusivity. We have these deep trap states, which unfortunately in the long range slow things down a little bit, but of course no grain boundary resistance because it's an amorphous glassy material. So I'll just end off in the last 5 minutes talking about some mechanical properties. This shows the aluminum chloride, the niobium chloride, and agurudite all pressed at 120 megapascals for 3 minutes. And you can see that there's pores in the agurudite. We normally would one press at a much higher pressure, but we did this in particular so we could compare the three. And you can see at this situation, the layoc is completely dense, and the LNOC, the niobium oxychloride, has a little bit of pore structure. And Max Palmer and Jeff Sakamoto's group measured the hardness of some of these materials, and you can see that LNOC and LTOC are about 0.4 gigapascals compared to agurudite, which has been measured by Matt McDowell's group to be around 2, and layoc is even much lower at about less than 0.2 gigapascals. And Vipin Singh in my group, who's working on these materials for some time, also has just shown that when you take we're measuring resistance versus stack pressure. When you release this for layoc, again, there's very little change in the resistance, whereas for the lithium tantalum oxychloride, there's a distinct difference. So this, as I said, really is viscoplastic. The layoc and LTOC is not. And this just shows how what a cross-section, a fib cross-section of the cathode looks like, showing the intimate contact that one has between the layoc, the viscoplastic solid electrolyte, and the cathode active material. Same picture. And again, this is now at low pressure of 3 megapascals. And you can see that the cycling stability, these don't work quite as well at 3 megapascals as they do with a higher pressure, but it's still, this is without isostatic pressure. And so this, we believe, is really quite hopeful. And it is also of interest then to compare the high pressure cell at 200 megapascals with the low pressure cell at 3 megapascals. And you can see that the first discharge here is even higher, capacity of 180 versus 160 for the higher pressure cell. So the bottom line here is that it's not necessary to achieve good capacity in these systems. It's not necessary to go to really high pressures in these cells. Now, of course, we still have to work a little bit more on on getting these materials to cycle well and carrying out some more creative things at the negative side of the cell. And just to end off, we've been working with Jess Sakamoto's group to use garnet as a negative electrode. So in this case, we're using lithium indium with an interface of agirodite, and we're trying to swap this out by using a garnet instead as an interface. And this just shows some data from my grad student, Vipin Singh. This is a Nyquist plot showing the data for LAOC. We can identify three components, three processes in the impedance in the EIS. A high-frequency component, which is the bulk solid electrolyte, a medium-frequency component, which is the grain boundary between the garnet and the LAOC, and this low-frequency component, which is our heteroelectrolyte interface. And when we do this as a function of stack pressure, you can see that we're able to achieve resistances of less than 100 ohm centimeter squared over very, very low stack pressures. So we think this is rather exciting as well. So then, take-home messages. Hope I've convinced you that we achieve good oxidation stability of both the halide and the oxyhalide electrolytes, which allow us to pair these with high energy density, low-cost cathodes with no coating on the surface. In particular, many of these materials have a low lithium fraction, which makes them appealing because one can reduce elemental cost in this fashion. And this just compares carrier concentration in some well-known solid electrolytes, such as LGPS, that all have similar conductivities with the low concentration in the lithium niobium oxychloride. And I hope I've described, or at least highlighted some design principles for these nanocrystalline amorphous materials. I think we've really established what to do with crystalline materials, but these are much more difficult in terms of achieving design principles. What seems clear is that mixed anion coordination is important, which leads to frustration. We believe that many of these materials really benefit from the role of anion dynamics to create a flex ion framework. And finally, of course, there's probably a trade-off between ion conductivity versus mechanical properties. And so it remains to be seen as to whether we can get some of the viscoplastic materials like LAOC to achieve conductivities in the order of 10 millisiemens like we can for the chain oligomeric structures. And I'll just leave you with a thought of whether perhaps these molecular by design, as we call them, solid electrolytes, be a compromise between the traditional polymer electrolytes, such as PEO, and the other types of rigid conductors that we're more familiar with. And so I think that this area of these disordered materials is basically encompasses a vast space to be explored. And I hope I've inspired you to do that. So I'll just end off by thanking all of the people that worked on these projects over the years. Our halide work was started with Kavish and Dr. Kern-Ho Park, and Kavish is now at QuantumScape and Dr. Park at Kete in Korea. The work on the LAOC was done by Insang, Baltej, and Yubo for the large part. Lidong did a lot of the halide work. Well, all of these people have contributed in many ways, and Vipin has been working on the garnet cells. And our other collaborators, of course, have been instrumental in helping us. And this just shows a picture of my group with some people missing, highlighting some of the people that contributed to the work here. And again, I'd like to thank my funding agencies for their support over the years. And thank you for your attention.
Thank you, Linda. I would say, and thanks for walkthrough of both rather well-known materials in a very pedagogic fashion, and also highlighting some very new things. I think it's been a walk through both fields, and I was very impressed. I have seen now that there are a few questions in the Q&A. We'll bring those up first, and then I have some questions of my own as well, of course. And we see that people are still adding questions, and don't hesitate to do that. We had more than 120 attendees this afternoon here in Europe, in more early morning hours in Canada. So we start off with a question from David McNulty from the University of Limerick in Ireland.